I got stuck at the Vista Verde school fair that my son was running, and I got stuck on the booth where I had to take down a whole lot of entries for kids trying to win a big jar of fortune cookies, and they had to estimate how many fortune cookies were in the jar, and the one who got the closest wins. So instead of seeing this as a parental chore at a spring fair, I saw this as a data collection opportunity. And so this is what the set of predictions that they made. You could see predictions and a couple of clowns. One kid, I remember him, who guessed 1,465 and a half fortune cookies in the jar. So this is a standard wisdom of crowds problem, and the standard sort of solution would be to apply some statistical summary of the distribution of answers that you're getting from the individuals here, and two obvious ones would be the mean and the median. So the mean's there in red and the median's there in blue. I don't remember the exact number, but it was very close to 100, and the median was within 1 or 2 fortune cookies. So the standard statistical wisdom of the crowd event held up. So what I'd like to talk about today is wisdom of the crowd's problems that in some way or other are more complicated than that and aren't so amenable to straight statistical solutions, but involve or are amenable to some sort of cognitive modeling approach where it's not easy to apply a simple statistical method to put together the wisdom or the knowledge of the crowd, but some deeper understanding of the cognitive processes and the cognitive representations is required. And so I have 3 case studies, I guess, all of which try and play into this broad point that sometimes cognitive models are useful for aggregating what it is that people know. So the first one's going to deal with a real-world example of probability estimation in football or soccer games. Another one's going to be about strategic competitions, and we actually heard a little bit about this already. And the third one's going to be in a dynamic decision-making environment. And that's actually something I don't think anybody's talked about so far. Okay, so we wanted to study probability estimation. We've already heard a bunch about this morning. We wanted to be somewhere in a useful range, and we wanted to avoid 2 ends. So if you're asking people to estimate probabilities, one thing you can do is get probabilities that you could actually just look up on Wikipedia, and we didn't want to do that sort of thing, because if you can just look it up on Wikipedia, what's the point in going through a whole wisdom of the crowds exercise? Or you can do the sort of forecasting ones that we heard about this morning. What's the probability that Iran's going to launch a missile or something? So they're interesting, and people could say 70% probability. But as was pointed out this morning, you only learn so much when that event does or doesn't happen. And you need a lot of these to get some feel for whether people are accurate. So what we decided to do was to pick something that we think is somewhere in between that. This is work with Irina. I'll acknowledge everybody at the end. This is with a lot of collaborators throughout. We had a look at 6,000 plus soccer games, first division soccer games played throughout the world over the last 10 years or so, and calculated a whole lot of a statistical characterization of that real world environment, if you like. So what we had was the sequence of goals scored by home and away teams and what minute each of these goals was scored in. Here are a bunch of analyses that you can do to characterize a real world soccer environment. So you can see up in the top left there, the distribution as the game progresses from 0 through 90 minutes. In blue, that the team that's currently ahead will win. So if a team's ahead at a certain time, what's the probability they go on to win the game? And you can see all sorts of other statistical distributions related to goal scoring sequences and so on.
Are these empirical distributions?
So these are empirical distributions, and so now the idea is we can ask people to estimate a probability. They couldn't look it up easily on Wikipedia, but we can measure whether their probability is right or not as a binary event that either becomes true or not true, but relative to these empirical ground truths established from this database. So in fact, that's exactly what we did. We used Mechanical Turk. We got 145 people. First of all, we got them to self-rate their expertise, and then we gave them some general knowledge questions. But the meat of it was in 40 probability estimation questions, all of this sort of form. So a team's ahead at the 5th minute of game time. What's the probability they'll go on to win the game? So people can answer and give a probability estimate to that. And we can empirically look up from the sorts of analyses that I was just showing you what the empirical ground truth for this is. And that turns out to be 59% for this question. So people did a whole lot of these questions. And what we would like to do in a wisdom of crowd context is try and put together the answers of these 145 people and see if we can combine their knowledge in some way to get better answers that are closer to these empirical ground truths.
So you didn't say which team, you just said some teams. Some team is ahead.
There are 40 different questions. Some of them are specific to the home team. So one of them would be, what's the probability a soccer game will be 2-1 at halftime with the home team ahead or something. So all sorts of different questions like that.
They in their head go uniform across all teams of that type.
Yeah, so it would be, you're thinking of, we gave them a little bit of context of the environment. So, you're thinking about all first division leagues played in, Okay, so we're going to build a cognitive model to try and put together all of these probability judgments that people are making. And this has a lot of similarities to some stuff Mark was talking about yesterday. So there are 40 of these, pi 1 for the true or the empirical ground truth probability for the first question through to pi 40 for all of the questions. And a straight statistical characterization would just be to try and estimate these things by a mean or a median or something from the raw data, but we're going to use two psychological insights, both of which have already been talked about at this conference. One is that there might be individual differences in the expertise that the different people on Mechanical Turk had. So one way of modelling this, very similar to the way Mark presented yesterday, is that we assume when people give their probability estimates, they're centred on the ground truth, but they have a standard deviation that corresponds to their level of expertise. And in particular, people who are more expert have lower standard deviations. We assume they have the same standard deviation for all of the questions, so they're equally expert or non-expert across all 40 questions. You could obviously extend that if you wanted to, but for now, equal expertise within an individual, but different expertises across different individuals, so that if you have a larger standard deviation, as in person 2, you're giving less precise answers. So the first psychological assumption built into the model is that there's different levels of expertise. And the second one, which we've already talked about today, is the idea that people misperceive, or there's some sort of calibration function that maps the true probability, the empirical true probability, to the one that they perceive. And in particular, the overestimation of rare events and the underestimation of frequent events.
That's a question. So there's at least two ways to talk about expertise. One is in terms of the amount of variance in the judgment, and the other is in terms of the location. So you're assuming the locations are all accurate?
Yes.
But the variances are the only difference?
That's exactly right. So we're entirely loaded on that one sense of the variability. That's right. So these are the two psychological assumptions we want to build into the model. Here's a graphical model that does this. For people who like or know graphical models, this actually tells you everything you need to know. For people who don't like or know graphical models, it really just captures exactly what I was showing before. What we're building is a model of the way people produced behavior on the task. So nowhere in this model is the empirical ground truth presented. This is all just done modeling the behavior that people produced. And so it's an account of the probability estimates that the 145 people gave to the 40 questions that we asked them about. It's driven by the latent ground truths that we would like to know. These are the things we want to infer. This is doing the calibration function mapping with a prior that does the over and underestimation, and this is the individual precision or the individual expertise. And so once you've specified this thought process for the data, Bayes does everything else for you. You now just run sampling across the graphical model and you get a full joint posterior distribution over everything you would like to know.
Those are your priors?
Those are the priors. Yeah, specified without looking at the data. Genuinely did this properly. So in particular, what you're going to learn is an estimate of the crowd's aggregate through this cognitive model. This will be the aggregated knowledge that will be the estimate for the probabilities for each of the 40 questions. You're going to learn something about how every individual is calibrated, and you're going to learn something about how expert they are. So how well does that work? Here's a graph that shows everything. Maybe I should have built this up. If you're looking at the average error, so the mean absolute deviation between what people said and what the true empirical truth was across all of the questions, that ranges from about 13% up to about 40%, or 0.13 up to 0.4. You can see the distribution of people's answers with the little stick men as before. You can see how the mean performs. So if you just took the average of all of those P's, that falls here, and you can see a scatter plot showing the relationship between what it said and what the truth was. Here's how the median performs. Now you start adding in the cognitive models. If you do the full cognitive model that I showed you, that performs the best and starts being among the very best of all of the people in its estimate. If you relax one or other of the psychological contributions, so it's easy to run one that just has the individual differences without the calibration, or just has the calibration without the individual differences, you do slightly worse. And so combining both of them leads to the best answer. Yeah, Bill.
I wasn't sure what your bias was. The bias, it's not the linear log odds.
Yeah, it's the linear log odds, but the one parameter version that just does the under and over estimation.
0.5.
This is a prior prediction from the model. So this is what it expects to see. And these are 95, 99% credible intervals. Okay, so it's exactly that the model expects to see. Okay, so that's what the model does in terms of its prediction. Yeah.
So the unusual thing here is that you infer the calibration function in an unsupervised fashion.
Everything here is unsupervised. It never ever sees anything to do with the actual answers. That's right. We're just modeling people's behavior, and from that we're making inferences about what the signal is that's driving them. Casey?
What is the function, the form of the calibration function?
It's that linear and log odds function, but the one parameter version that is just doing under an overestimation, not the shift.
It's the Karmarkar function. P to the alpha over P to the alpha plus 1 minus P to the alpha.
Did Tom show this earlier?
Yeah.
Yeah.
No.
Well, yes, but
You showed the two parameters.
in the two-parameter version, so the multiplicative parameter set equal to 1. That's what it is.
The easiest way to think about it is just, here's the log odds, so this is centered at 0 if it's a half and then goes positive and negative, and we're scaling that by something that's a bit less than 1, so we're just shrinking things back towards the middle.
Lambda corresponds to sigma?
Lambda's a precision, so, yeah. I write things in terms of precision, so sigma is the reparameterization of this precision. That's right.
There's 1 over 0.
Square root, so standard deviations. And, yeah. Okay, and so here's what else the model infers from the behavior. So I've shown you what it did with the pies to get the estimate. Here's what it does for 4 subjects evenly spaced through the inferences it made about delta, this thing that does the shrinking. So it thinks that some subjects are well calibrated, right through to subjects that it thinks aren't well calibrated at all. So it makes inferences about the calibration functions of individuals. And then here's the version of the slide that Mark thought was surprising and Tom thought wasn't surprising. So this is the relationship between the standard deviation and the revealed mean absolute deviation once you look up the answers. So this expertise is the sigma, which is the 1 on square root lambda. And so this is showing each dot is an individual. It's showing their inferred level of expertise, how well they actually performed. Once you go and look up the answers, and you get a very strong correlation between the two of them. If you look at the self-rated expertise and the general knowledge questions that we really gave as part of an MTurk check as much as anything to check people were doing the task, but there's nothing in here. If anything, it goes in the wrong direction with people who thought they were better at soccer doing worse in the estimation. Okay, so this was an example of using a cognitive model of people's behavior, modeling how people produced probability estimates in the task to make inferences about how they were calibrated, how expert they were, but most particularly to put together all of their probability estimates sensitive to individual differences in calibration to get a wisdom of crowds aggregate that outperforms simple statistical methods. So there's example 1. Now I want to talk about strategic competitions. This plays in a little bit to some of Jack's stuff. So suppose we only had 3 people, and that's our crowd, and we want to make these 3 guys wise. How are we going to do this? So how do we get accurate estimates from really limited resources? If you're not happy with these guys, imagine the 3 guys who sit on the foreign desk in American affairs, and these are the ones who are always going to get polled, but they all read the same sources and they talk to each other every day. So that, these are not independent people, but they're the 3 you have to extract and combine the knowledge from. So we did it with things like this. People were estimating now the prices of household objects described in this way in a couple of carefully designed sets, so that we had 22 people estimate the prices of 50 household items, 2 different sets of household items, careful control over the distribution of prices and randomized orders and all that empirical good stuff. So how does that go? If you look at individuals, on average they were $9.45 away from the true price. And so this shows the true price and the estimated price on the y-axis. Every dot is a person, and then the mean absolute deviation is $9.45. So that's a summary of how individuals did. If you just average together for every item that was judged, take all the estimates that anybody gave, average all of those together, how well does that do? That's a standard wisdom of crowds. That gets you down to $7.52. But of course, this is averaging across many people, and what we're interested in is how well could we do if we just had 3 people, not the full crowd. So these, if you like, provide the endpoints. This is how well one person does, this is how well everybody does, how well can we do with 3 people. So if you just take all possible subsets of 3 people, this is what you get, and it comes down to $8.02. If you prime a single person, telling them what 2 other people said, so grab 2 out of the database, show them that to give them some suggestion, and then ask them for their estimate, so that's kind of 3 people's worth of judgment. If you like, that gives you $9.36. If you put 3 people in a room and get them sequentially to give estimates and then average those 3 estimates, that gets you down to $8.82. If you then tell those people now you've got to agree with each other, so go through some sort of consensus process until you produce a price that you're all happy with, that doesn't change things very much. It's still around $8.80.
What's the difference between the top one and the third
In the top one, the 3 people were completely independent, process independent, and David's was. In the last 2 ones here, there are 3 people in the room doing this in some sort of collaborative setting, physically co-located.
Is that on Mechanical Turk, or is that?
No, this is in a lab over here, the one with no windows, because it was designed by a vision scientist and they hate light. It was also used as the prison in Conquest of the Planet of the Apes, if you go into it. Okay, so all of those approaches with 3 people relied upon consensus. The other thing we could do is make people compete. We've already talked about that a little bit at the workshop. So we needed some sort of competition that we thought our undergraduates up in the Planet of the Apes building would understand. So we turned to the Price is Right. And this is the Price is Right one that gets you from the beginning up onto the stage, where you see a prize and you bid in sequence, hearing what everybody else says. The one who's close as possible to the true price of the prize without going over is the winner in this game. So these rules are understood. You bid in sequence, closest to the correct without going over. And so we played this game over and over up in the lab, rotating the orders, counterbalancing everything. This is interesting, and the cognitive models are needed here now, returning to the main theme, because now what people say is not necessarily what they believe. They're now in a bidding competition where the rules are clear, and there are strategies that can come into play that disconnect what you believe into what you say. In other words, a cognitive process is operating that mediates between those 2 things. So for example, if these 3 guys believe that the price of the prize is between $8 and $16, and the first guy says 15, and the second guy says 12, then the right thing for the third guy to do is to say $1. That's the rational thing that will maximize his probability of winning the game, given the belief that the price is somewhere between $8 and $16. Because of the nature of the game, where it's as close as possible without going over. Really, he's just hoping that 12 and 15 have gone over, in which case there's no reason not to go all the way down to $1. Okay? But it's not because he believes the value of the prize is $1. So this needs a model, and the model here is fairly straightforward, or at least a first pass of it. The idea is that what people are doing when they bid is taking what they know, seeing what the other people have bid, and making the bid that is the one that maximizes their probability of the game, given all of those things that they know, their assumptions about the value of the prize and the bids that they've already observed. So you can work your way through this in a fully recursive sort of way. So the last person's kind of easy. Here's what I believe. Here's what's been bid. Where do I go that maximizes my probability of winning? For the second last person, I've already seen one bid. I know what I believe. I'm going to assume that if I bid here, the next person is going to rationally respond to that. So if I go here, they're going to go here. If I go here, they're going to... Which one of these maximizes my probability of winning the game? Then for the very first person, it's if I go here, then they're going to go here, and that'll make them go here. And you think through all of these possibilities. So a fully sort of recursive version in which everybody is trying to maximize based upon an assumption about what the value of the prize is. Okay, so we did all of that. That's a whole lot of number crunching and fairly hard work, which is one of the reasons it was only 3 people, not 4, like in the real Price is Right, and why it only went up to $50. But we managed to crank through it doing it that way. Yeah.
Is that a strong assumption there, the shared knowledge?
Yeah, the shared knowledge is a strong assumption. Yeah, it's, yes. The reason it goes like that is, the way we're going to use this model now to make a combined decision or get a wisdom of the crowds type aggregation process going is we're assuming that that's the way decision making works, that there's some shared knowledge and people are bidding to maximize their probability of winning the game. Now we've seen their bids, Bayesian inference tells you what the price distribution, what the uncertain knowledge about the price must have been for those bids to have followed under the assumed rational bidding process. So that's what's happening here. It's working its way across all possible price ranges that could be the uncertain knowledge that people share under this assumed model, and working out which one of these price ranges is most likely to have generated the observed bidding behavior that we see.
Is the shared knowledge always uniform over a range, or did you look at other?
We looked at a bunch of different ones. In fact, I'm going to present some real-world data in a minute where there was a slightly different assumption. So we've had Gaussian type ones, uniform type ones. I don't think that's the key weakness. I think the key weakness is the one Casey pointed out, where this doesn't allow for any individual differences at all. We can't allow for too many individual differences, otherwise the model will just start becoming unidentified and you won't get any interesting inference, but we are at the very strong end of a shared knowledge assumption. Okay, so the question is, how well does that do? So we did that with all of the real-world data that we had, and now we get down to $8.05 away. So let me show you the results of all of those in one nice display. I think this captures it nicely. So the black line corresponds to the mean absolute deviation as you move from 1 through to, and it's starting to asymptote even at 10 people already. So that's as you just average an independent crowd, the black line. Now you can look up the mean absolute deviation you got by these various methods that involved 3 people's worth of information. So the primed individual or the cooperative averaging or the consensus, and you can look at the competitive Price is Right one. And by mapping down on this curve, you get a measure now of sort of how many independent people's worth of information did you get out of all of these methods of combining 3 people who are in the room or somehow together. And so you can see the clear result here, all this priming and cooperation. You're not even getting as many people who are in the room. But the cooperative is like 1.5 independent people's worth of wisdom of the crowd effect. At least with the competitive one, you recover 3 fully independent people. And so one conclusion from this would be, because these 3 people are all very, very highly correlated and know what each other is doing, you're not going to get the easy wisdom of the crowds effect, but at least if you make them compete, you don't lose out and you still get your 3 people's worth. So the suggestion would be, if you've got 3 people who are in a room and the only one's available, but there's no way that they're independent, you're better off making them compete with each other than getting them to cooperate to extract all the knowledge out of them. Yeah.
Sorry, I think I missed something this one. Why are they giving, if they have shared knowledge, why are they giving different answers? Like there's an underlying error as well?
In which of the conditions?
Let's say in the, I'm sorry, like in the cooperative, or like you just get 3 independents and you average them?
Because it's uncertain knowledge.
But if I know the range is like 8 to 16, why don't, and it's uniform, why don't I just guess 12?
You could. You could. And all three people could say 12. And then empirically, that doesn't perform as well as getting them to compete.
But isn't that the best guess if it's uniform? Is the 12? Isn't that going to minimize absolute deviation? Or maybe not?
Yeah, okay, so maybe put it this way. What's almost certainly true, and what has to be true for the wisdom of crowds to be interesting here, is that there is some difference in the knowledge that people have. In which case that assumption of perfectly shared knowledge is model misspecification and wrong, but nonetheless useful because it outperforms these other cooperative or simple statistical ways of bringing things together. Yeah. And it actually strongly suggests that something that did allow for these variances in knowledge in the competitive approach would do even better.
And this was an experiment, right?
Yeah, this is all empirical.
I'm sorry. Okay.
So this is an empirical evaluation of things.
Yeah, got it. Sorry.
Right. Okay, in the real world, I hesitate to call the Price is Right the real world, but you see this sort of strategic bidding behavior all the time. So I had an undergrad who was still talking to me, watched 273 shows of this in 2009 and write down all of the prizes. The bid of $1 right at the end is something that comes up very often in this game. And in fact, there are other sort of interesting strategic bids. I don't know if anybody's ever seen this on YouTube, but I strongly recommend it. The guy who, no matter what the prize up on the thing is, just says 420 every time, with his stoner mates laughing up in the background and Bob Barker having no idea what's going on. So the point is, people don't always say what they believe about the price of the prize. And so we tried a modified version of this method, actually, with different assumptions, uniform assumptions, and we couldn't get the calculation crunch to go far enough to go back through all of the players bidding strategically, but we got back through the last 2 bidding strategically. So what you're looking is the performance in combining the knowledge to get an estimate of the true value of the prize, both in absolute terms and in relative terms, so normalizing for the price of the prize, although it doesn't make very much difference. And what you get out of this, well, so there's a whole lot of ways of doing it. You could just take 1 bid at random, or you could take the 2nd bid or the 3rd bid, or you could just average the bids, or just average the middle 2 bids, or all sorts of things you could do. The general results you get out of this is that methods that involve some sort of aggregation are always better performed than ones that just rely on a single estimate. So that's the cluster you can see down there. And then the methods that think about strategic the methods that are model-based or try and model the decision-making process outperform the others, but only if you build in this strategic component. So you allow for the idea that people are bidding to maximize their probability of winning the game and not necessarily reporting exactly what they believe. And so the 2 best models that we got were the ones that were very similar to the one I just explained for the empirical small-scale laboratory setup, where we're assuming that the last 2 players are bidding strategically to maximize their probability of winning. So that was my strategic competition example. Now I want to move to the, yeah, Casey.
What is the intuition for why that model works so well.
The intuition for why that model works is if the last person says 1 and you throw 1 into some averaging process, statistical averaging process, that's going to skew things horribly. They didn't say 1 because they think that the $600 fridge is worth $1. They said it for strategic reasons. And so the model, by understanding the strategic decision-making process that led to that behavior, will say this is consistent with them believing that it's between $500 and $600 and that the others are overestimates. Okay, so its inference will be that's what must have produced the behavior. Yeah.
Can I say one thing? So I think another way to say the same thing you said is the distinction probably between, say, many of the psychologists in the room and those who aren't psychologists, is the psychologists often will distinguish between the latent judgment and the expression of that judgment as it's processed through other considerations.
Right.
And not assume that the expressed judgment is always equal to the latent judgment.
And so that's also true of the calibration function. The idea is you misperceive a very rare event and judge it to be slightly more likely than it is. And so mapping that back leads to a better estimate of the true thing, which is ultimately what you're going to be measured by. Yeah, Dan?
Does this result imply that one person could do better by competing with themselves? So if you're the first bidder, then you say, okay, what am I going to bid now? Suppose the first person bid that and I'm the second person, what would I bid? Now suppose the second person bid that and I'm the third person, what do I bid? And then sort of aggregate those.
That's, I mean, it seems like mentally hard work, but it seems like a good idea. I'd never thought about it, and it actually combines this sort of stuff with the type of stuff Stefan does, the wisdom of crowds within. It's a nice idea. I hadn't thought about it.
And then which person gets the prize?
Well, you always win, don't you? Yeah, David.
And did your subjects have more fun in that game, the Price is Right game, as opposed to just answering this question?
Yeah, so I'm sure the Price is Right was more fun. I don't know how you control for motivational things and this sort of stuff. They weren't having that much fun, okay. You know. Okay. Anything else before I move on to the last one? So the last one I think is the one that's least worked out, but I think it's in some ways the most interesting, or at least the most novel. So this is called a Bandit Problem, thanks to Mark for the animation. The idea here is there are 4 buttons. Each of them are going to give you a green with some fixed but unknown rate. So you get rewarded at some fixed but unknown rate across all of these buttons, and each button has a different unknown but fixed rate of rewarding. And what you're trying to do is maximize the number of green rewards you get over a known fixed sequence of button presses. So you know that you get to click 16 times or something like that. And so you start off exploring around looking for the ones that provide the most reward, but as you get towards the end of the sequence, you start exploiting the ones that you know empirically to be at least reasonably good. And so Bandit problems have this natural, interesting psychological element of when you move from an exploratory to an exploitative strategy in sequential decision making under conditions of uncertainty. But notice that there's an inherent stochasticity to the way this game plays, and in particular, even if the same person with exactly the same settings and the same decision strategy or heuristic plays it, they're going to end up in different game states every time because you get different sorts of rewards that will lead the same strategy to do you in different things. And there's a very, very large state space that's going on for any, this is 4 choices and 16 trials, very, very large state space. So now if you think about how would you do wisdom of crowds for a dynamic decision-making task like this, it's not going to be as simple as I'm in this state, let's look up what decision the majority of the crowd made when they're in this state, because that's going to be extremely sparse. There might be nobody who was ever in that game state, even for people who are behaving quite regularly. And so the challenge is, how do you do aggregation there? There isn't a mode or a mean or a median or anything that you can do. You're going to need a cognitive model so that you can understand what parameters were driving the decision making and average that across people. And let that be the play. So that's the motivation. So the data we had, 451 people played 24 alternative games. The optimal decision-making strategy for this is well known, and you can calculate it via dynamic programming. It's something that goes through looking for maximizing the expected reward and stepping that all of the way through. So we know what optimal decision-making looks like for these games. Here are 4 different decision-making heuristics, all of which developed in the literature one way or another, all of which are fairly simple and are interesting in their own ways. So win, stay, lose, shift is the classic one, where you, if you get a green, you stay, and if you get a red, you shift with some probability. You could have an extended win, stay, lose, shift that says staying after winning has a different probability from shifting after losing. There's a standard machine learning or reinforcement learning one called epsilon greedy, where most of the time you choose the one with the greatest frequentist reward that's observed, but explore with some probability. And another one called epsilon decreasing, which is the same except that your probability of exploring decreases as you progress along the number of trials. So those are all interesting psychological models, and it's possible to infer the parameters of those models from the behavioral data that we have. So here's another graphical model. This is for the extended win, stay, lose, shift. And we're doing this now in a hierarchical Bayesian setting. So this is what button the person pressed on the ith trial of the jth problem they did if they were the kth person. These are all the behavioral data that we have. We're interested in the choice probabilities they had for doing each of these button presses, which come from this probability of staying and when you win and shifting when you lose, that are assumed to have population level distributions that you can learn about. So you have a model of individual differences that allows you to learn at both the individual and the group level the parameters of this model that are most consistent with the decision-making behavior that's observed. Okay, and so once you've done all of this inference, you now naturally have a group player. If you wanted to say what the crowd overall would do in a specific game situation, you can draw parameters from these group level distributions and let that play its way through the game. Okay, so you've effectively, in doing this hierarchical modeling, combined everything that you knew about people's behavior, combined it in this compressed parameterized form that drives the decision-making model that's assumed to produce the behavior. And so you can let that group decision-making model play the games, and you can compare it to human performance and optimal performance, and that's what this curve does. So here's the number of rewards obtained, more is better. The little histograms correspond to what the 451 individuals did. This is the optimal performance. Of course, this isn't a single number because it depends upon the luck of getting rewards or not getting rewards, so this is the distribution if you apply the optimal decision-making process. And here's what the group player does if you use the extended win, stay, lose, shift heuristic. And so here's the strong result. What we did was try that with the 4 different models that I talked about. So this is the one that I already showed you. You can see what it does with those other 4 heuristics, and the strong result is the one down on the bottom right, which is when you use the epsilon decreasing group player, you now, based upon people who perform this way, are able to infer a group decision-making player that has this distribution of performance which pretty much matches the optimal. So you're now able to combine a whole lot of people who are underperforming, but combine their knowledge through the window necessarily provided by the cognitive model to now match the distribution of optimal performance. And we got this in a number of different domains. One thing that I find interesting and part clear and part puzzling is that we have quite good evidence from a different analysis that there's no way this heuristic was the one that best described human decision making. The extended win, stay, lose, shift actually looked like a much better account of what people were doing. Nonetheless, it's not the one that leads to the best group player. Part of that's clear because extended win, stay, lose, shift can't at any parameterization mimic optimal behavior very well, whereas epsilon decreasing can mimic optimal behavior fairly well, but why it should still work when people aren't using it is something I find a little bit puzzling. Yeah, Bill?
Does the model say each person is one of those kinds throughout the whole game?
We tried a number, throughout the whole, yes. I thought you were going to ask a question about whether we tried blending different people across different models and putting that together, and we did, but it didn't lead to any significant improvement. But yeah, there's an assumption of stationarity both in the decision-making process and the parameters of that decision-making process. There's nothing adaptive here. Yeah?
Maybe the reason why the epsilon decreasing algorithm really works to model what the optimal solution would be is because every time you press a button, you're getting a sample that gives you a bit of information. I guess if you model it from like an information theory, you're peeking into this unknown space, getting some information about what the distribution is, and maybe that just models the optimal way to figure out, do you have more information given what you see already from your button presses, or is there more information that you should sample from?
Right, so I think another way of saying that is every model and its parameters provide a window or a summary onto human decision making, and it's a particular window or look depending upon the assumptions in the model. And so the more people you get to see, the sharper your view through that window is. It's just not crystal clear to me why a window that's clearly the wrong window just in terms of describing human behavior still works so effectively. I think that's the bit that puzzles me. Yeah?
It may have been already answered, but did people shift their strategies at all would they start out in one mode because it's kind of simple to think about, and then move on to a more complicated mode of strategy?
I can't give a very complete answer. It wasn't something we were looking at in the study. I know how you could look at that, but we didn't do it. The part answer that I can give is because we did the model comparison testing whether all 4 of those models was the best account of each individual's behavior. If it was the case, for example, somebody did extended win-stay lose shift for a little while, but then just resorted to win-stay lose shift for the last half, the natural thing that would happen is an uncertain inference as to which of those 2 models the individual belonged to, under the assumption that it was the same one the whole time, right? You would be, could be 50%, and that almost never happened. People, very large modes, very confidently assigned to one of the 4 models only. So that's not a proof, that's just suggestive that if it was going on, it wasn't massive. Doesn't mean parameters couldn't be drifting, doesn't mean there isn't a bit of it going on, but it does suggest that there weren't very clean switches from one model to another.
So, I'll finish.
It's going to be very easy to finish. So I tried to talk about 3 things where you need cognitive models. Just to remind you, I talked about the soccer probability estimation one, where building in individual differences in calibration helped to provide a better aggregate. Talked about very small crowds and strategic competition, where the idea that people have to compete against each other, but you need a model of the bidding process that's mapping what they know into what they say was important, and Bayes lets you undo that so that you can get a good average from the bidding process. And then the dynamic decision-making environment, where the motivation is you can't collect enough data to do any sort of empirical averaging at the data level. You need a cognitive model to map it into latent psychological parameters, the information across which can be combined. Okay, so then I need to thank Collaborators, Mark, for all of this stuff really, and especially on the Bandit Problems. Shunan is here from up from San Diego, which I appreciate, for Bandit Problems and Prices Right. Jenny's the poor one who had to watch all of those episodes of Drew Carey, and Irina, who's here, who's been helping me with the soccer probability stuff. Thanks very much.
Michael, could you go back to that slide where you had the optimal, the distribution of the optimal policy for that Bandit problem?
That one?
Well, yes. Where would the curve be if you, for instance, for that epsilon decreasing strategy, if you found the best thing you could do under that policy?
The best
Given
thing?
you know the underlying distribution of the 4 buttons.
The underlying, you mean the distribution from which the 4 were independently randomly sampled? Mm-hmm. That's the green line.
Isn't that the optimal policy?
Yeah, sorry. What, oh, did you say epsilon decreasing? Maybe I missed the question. Say it again, please.
So epsilon decreasing, that's not the optimal policy,
No, it's
right?
not. So say the question again.
So there's a model that
Yes.
says I should use an epsilon decreasing
Oh,
strategy.
do you mean it?
If I could optimize that model,
Yeah.
what would the distribution of returns look like?
We had that at one point. I don't.
Wouldn't that be interesting to compare?
Yeah. Yes. I don't know whether you remember, Shunan. So the way we got at that stuff is the intuitive way to do it is the optimal player produces some behavior, fit the epsilon decreasing or infer the parameters of epsilon decreasing from that optimal behavior. So you've now seen what an optimal player would do. What does that look like through the window provided by epsilon decreasing? So what are the best parameters you could have? You know, if you were constrained to use epsilon decreasing, that's the only decision process you can get in your head. What would be the right parameters to use?
Because it'd be nice to see if at least the group beats that.
Yeah.
Or how far off that is.
Yeah, well, for epsilon decreasing, it's not going to happen because everything's at ceiling. But for all the other ones, it's extremely interesting. And that sort of stuff is actually useful. We haven't talked much about training, I guess. I'm not quite sure how much that's a wisdom of the crowds topic, but it seems like a great potential for training to me. So if you give somebody a bandit problem and you say, look, optimally, you could have got 16 and you only got 13, do better, that's a lot less helpful than you're decreasing your exploration too early, you need to explore for a little bit longer or something, which is what you would get out of this, what an optimal parameter would look like and what your parameter currently looks like. Yeah, Bill?
The game is defined, I guess, by 4 Bernoulli parameters, right? One for each button. And if those were to vary around 4-dimensional space, does the strategies that you would want, these 4 strategies have differential payoffs and so forth?
Yes, but I don't know what it looks like. I mean, yeah.
But you ran it under one particular selection before.
Actually, I'm only showing you one, and this was uniform, but we did other ones with beta distribution so that most reward rates were fairly low, a sort of sparse, scarce environment, and other ones with plentiful environments, and people adapt to that and detect it, and we get exactly the same sort of results. There's a question here.
Can you please go back to the real-world decision
Real world. Does that mean Price is Right, or does that mean soccer?
The soccer.
Soccer is not real world.
The underlying assumption of the model was that there was going to be overestimating of rare events. And your participants were making their judgments based on their experience with soccer.
Yeah.
Especially the more experienced they were, this is probably what they did.
Right.
And we know from studies of experience-based decisions that underweighting of rare events is usually what's occurring. And I think this matches your data. So to what extent do you think this would improve your model to assume that they're actually underestimating the rare events? For instance, an event when the team that led the game at its early stages would lose the game. That almost never happens. I think maybe it's better, it can be seen better in the next slide where you explain the results.
Actually.
Yeah, they're very often below the curve, indicating an underweight of rare events.
I'm worried that I've flipped axes.
Oh.
Yeah, I think I have. I think I have. So
did they overestimate?
yes, because I'm sure I got truth right there. Yeah. So they're generally saying things that are bigger than they should. Yeah.
I see.
Right. So the truth is that it only happens 10% of the time, but they were saying 20%. The truth is, for whatever it was, it only happens 5% of the time or 10%, and they were saying it was 15 or 20.
So is it overestimation or is it regression looking at the other curves?
Well, I mean, it's kind of subtle, but when the calibration one kicks in, the gap, for example, here is a lot bigger than the gap here, so it looks as if it calibrated things back into the right corner and that helped. Or these things get bent downwards a little bit once calibration's applied. Yeah. But it's jointly interacting with the individual differences, at least in the one on the left, so it's hard to get clear intuitions. Yeah.
Going back to the other slide that you showed before this with the optimal
The Bandit Problem stuff?
With the dynamic decision making, yeah.
Yep.
And we had the 4. So I was curious to what extent are the data actually training the parameters over the prior? So what would just sort of the straight up untrained decision tools look like in their performance without using the prior? Is the data doing anything for you?
Yes, a lot. I mean, it would depend how hard we thought about the prior. And the truth is, with 451 people playing a lot of games, we didn't think very hard about the prior because it's not going to matter very much. But that's, say, unlike the calibration function one we were just thinking about, where I thought quite hard about what I expected the calibration to be, and so set something that had a prior predictive that I thought was good. So you could certainly think about this more carefully to think about what would be good prior predicted behavior before you ever saw the data was. The data are dominating here.
Oh, okay.
But partly just because we were lazy. Yeah. Ravi?
What were the specific individual differences that there was that model? And did any specific individual differences do better in terms of improving the model?
Which model?
The one with where the individual differences improves the...
In the soccer thing? Because of the assumption of the model, the question Tom asked earlier, we assumed everybody's centered on the right answer, modular calibration, but they're just more variable around the answer.
You didn't actually use the questions that you...
No, and this is constant for all questions, so this is the simplest possible starting case. You could extend this by thinking about systematic variation that people might have in their expertise, a much more richly structured expertise, certainly one that varied by questions, and because we had 8 different question types, it would be natural to tackle that as well. We haven't done any of that. Yeah?
I'm a little confused. So if I remember well, the optimal performance is to always choose the most probable button.
No, it's more complicated than that. In fact, it doesn't have a natural psychologically interpretable expression. You get it by having a very large dynamic programming search tree where you're looking out combinatorially at everything that could happen and projecting and choosing the one with the greatest expected reward projected over everything that could happen in the rest of the game. And it's not something where you can look at the current state of play and work it out easily.
So think about this shared knowledge assumption. I wonder if there's an alternative interpretation without changing the model at all. And so it's not shared knowledge, but the individuals differ in terms of where they're located with respect to the correct answer. So the variance is not in their noise function, but in their knowledge. It's not a different model, it's just a different interpretation of, and it sounds a little bit weaker.
Would it have implications? So in the end, you need a point summary of all of these things. You know, we have an inference about the distribution, the shared knowledge distribution, but you need a point summary. Would that interpretation change how you summarize?
Well, I don't think so.
I need to think about it, but maybe it doesn't. Maybe it doesn't.
So.
Okay. Yeah, Colin.
Relating sort of not to the specific model, but to the approach, it seems like we have two things at odds here in terms of searching for, this is for the dynamic model. We have two things at odds driving our search for models. So one is psychological plausibility and accuracy, so modeling the actual responses.
Right.
And then we also have this other task, which is how do we do best at the Bandit problem, or some kind of some other problem. Mm-hmm. So it seems like you're showing a success in terms of, oh, we found a psychological model that is does not well represent what people are doing, but it seems to be close to the optimal strategy.
In the sense of once everybody's aggregated together, you mean?
So maybe I'm missing the distinction between individuals and the group, but it seems like if you were trying to find different models, if you're searching for different models, it seems like if you're using a cognitive approach, you can say, okay, well, what are people doing? Mm-hmm. Let's try to accurately model that. You might use model fit, some kind of model fit type decision making. But then you have this other thing, which is how well do you do compared to to some kind of optimal decision making machine? Right. But so you're not using that to discover.
Well, the intention was that the two were related. So by having an account of the human behavior, so predictions of the decisions in a model fit type thing, you get inferences about psychological parameters that different individuals have, like how likely they are to switch, be the easiest one to think about. So you now have a collection of those for a whole lot of people. The wisdom of the crowds is to average together that latent understanding of when you should switch to get a group answer, an averaged answer to when you should switch, and that's what you're seeing as being the group player coming out. So the wisdom of crowds aggregation is at the latent level of the parameters that control the cognitive process, not at the behavioral level of the decision data they produced.
So you're taking the group group wisdom in one context, so one parameter of the group wisdom doing what they do, right, and then taking that parameter value and using it on a different algorithm that isn't what they're doing, or using it in a different process that isn't based on what they're doing, really.
Almost. If we have a little discussion, we can just flip a couple of words in that sentence and we'll be there. Yeah. David.
It just wasn't clear how you define optimal for this Bandit problem. Was that, or maybe you already said it, but is it assuming a certain prior over
Yeah, so it knows the true environmental distribution, the optimal player we're seeing here. Yeah. And we told people what it was to the extent they're capable of understanding that. Yeah. I'm hungry. You hungry?
All right. Let's thank Michael.